We're going to introduce this chapter on applications of integration by visiting a concept that we have already studied in Calc 1. So, depending on how recently you took Calc 1, this might be very familiar, and if it was a while back, it should hopefully ring some bells. In fact, finding the area under a curve is one of the ways we introduce the concept of integration. We understand integration on the one hand to be the inverse operation to differentiation, but it was also a way to find the area under a curve. And in fact, the areas was our introduction really to why we needed or would find useful a definite integral and not just an indefinite integral. So we get this, we start out, we've got theorem 6 here that says maybe I've got a region in the plane on some interval and that's bounded by some curves. And so this introduction says if f and g are continuous on the interval from a to b and g of x is less than or equal to f of x on the whole interval. So basically when we graph it, we could see that one function is always on top of the other function in this interval. Then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is given by this integral formula here. So we just integrate the difference f of x minus g of x from a to b. Now, I don't, most of the application formulas I don't really memorize. What I think of is how do I build this integral and how do I understand it from a building blocks perspective. So I'm going to introduce that by looking at this example. And I cannot emphasize enough this note here. You have to sketch the region. You have to know what the region looks like before you even begin to think about setting up an integral. And then there's this bit about drawing a representative rectangle. So I'm going to talk about that in a second when we set this up. So here we want to find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, x equals 1. So a lot of the problems will be worded like this. Find the area of the region bounded by, and then they give you like a list of equations. So two of these equations, x equals 0 and x equals 1, those are just vertical lines, and those basically will be the limits. But we want to make sure that we sketch the region so that we understand what we're looking at. And it doesn't have to be a perfect sketch, but we want to do our best to kind of get an idea of what it looks like. Feel free to use your calculator to help you sketch these graphs. These are fairly simple, so I'm just going to kind of do it by hand. The first function, y equals x squared plus 2. So that's just the x squared parabola, the regular, parabola pointing upward, but it starts up at 2 units up. So there's the vertex, and then it goes up. So let's see, I could sketch a couple of points here. So x squared plus 2 looks something like this. And then the other function is y equals negative x. So that's just the slope, line slope negative 1 goes through the origin. And the other lines are x equals 0 and x equals 1. So x equals 0 is the y-axis, x equals 1 is right here. Now, when we sketch this, there should be one region that is sort of properly bounded by just the curves, the equations they gave us. And there is a region that pops out here. It looks like this. So that's the region. And the next thing we want to do is draw a representative rectangle. Back in Calculus 1, before we did integration, what we did was this process where we would approximate the area under a curve by just drawing a bunch of rectangles that fit under the curve, right? And we could find the area of each rectangle, because length times width is pretty easy to do, and then add them all up. And so what we're going to do is pretend that that's kind of our approach here, but we're just going to draw one rectangle. What would that rectangle look like? It looks something like this. It doesn't matter if I draw it in the middle or to the left or to the right, but this is like what that rectangle would look like. It's a vertical rectangle. I'm going to talk about how sometimes we draw horizontal rectangles. I know that we need a vertical rectangle because no matter where I draw this rectangle, if I kind of slide it back and forth to the left and to the right through the region, the upper and lower bounds are always determined by the same function, right? So the parabola is always on top and the line is always on the bottom. It's a vertical rectangle, so it has a horizontal width. That means it's a delta x width. And then the length of a vertical rectangle is top minus bottom. The top curve is y equals x squared plus 2. The bottom curve is a negative x. So we're subtracting a negative x, and that gives us x squared plus x plus 2. So there's our length. So here's why a representative rectangle is helpful. I only have to think about that one rectangle right now. I'm going to find the area of that one rectangle. I'm going to call that area delta A, and it's length times width. So that length is x squared plus x plus 2, and the width is delta x, right? This is length times width. And if I can write the expression that gives me the area of this one rectangle, this sample rectangle, then the integral pretty much writes itself. So the area of the region, so notice I'm not writing delta A anymore, just writing A equals, it's the integral of this function, x squared plus x plus 2. The delta x turns into dx, and the only thing we're missing are the limits. The limits come from this region, and they kind of, they basically gave it to us, right, in the statement of the problem, x equals 0 to x equals 1. So we're integrating from 0 to 1. But in a physical sense, if we look back at our region that's outlined in red here, those limits come from, when I'm drawing vertical rectangles, they come from how far to the left could I push that rectangle and still be in the region, how far to the right could I push that rectangle and still be in the region. So they're really kind of, in a very physical sense, boundaries of the region. This is the hard part. The hard part is sketching, setting up the integral. This integral isn't too hard. It's a polynomial, so we can, there's no u substitution needed. We're just going to use the power rule all the way through. So using the power rule, we get 1/3 x cubed plus 1/2 x squared plus 2x. And I'm bringing my limits over from 0 to 1. And you might recall that when we evaluate a definite integral, we plug in the upper limit first and then subtract what we get when we plug in the lower limit. So plugging in 1 minus, and then what do we get when we plug in 0? Every term has a factor of x. So if I plug in 0, every term is 0, and the whole thing is 0. And so this is just 1/3 plus 1/2 plus 2. And that ends up being that's 17/6. Okay, so this is, how we want to approach these problems. Sketch first, figure out what kind of rectangles you need to draw, whether they're vertical or horizontal. and then draw your representative rectangle, and find the area, that sample area, and then that'll help you get the integral that you need to evaluate. Okay, let's try another one. We're going to find the area between the curves f of x equals 2 minus x squared and g of x equals x. So again, I'm going to start just by sketching these. You could throw these curves into, these functions into your calculator if you want some help graphing them. I'm going to just kind of do it freehand. 2 minus x squared is, you take the negative x squared function, so like the parabola pointing downward that opens down for right in the middle, and then it's shifted up 2 units. So there's its vertex. And then it does something like this. So it doesn't have to be perfect, but just sort of serviceable. And so there's the first curve, and then the next one, g of x equals x, that's just the line that goes through the origin with a slope of positive 1. Now they only gave us the 2, right? They didn't include x equals this and x equals that, right? They didn't explicitly tell us what the limits are. In the last one, they had to explicitly tell us what these limits are, right? Without them telling us x equals 0 and x equals 1, we wouldn't have the left and right boundaries. But in this example, just the 2 curves do define a properly kind of bounded region. And so we need to figure out what kind of rectangles. And then also we got to figure out where those limits come from. So take a moment, see if you know what kind of rectangles we should draw and why, and then think about how we might find those limits. You could pause the video if you want to work on that for a couple minutes before I start working on it. In this example, we do need to use vertical rectangles again. And it doesn't matter where I draw, it's just a vertical rectangle. I know that vertical rectangles will work because throughout the whole region, the top curve is always the parabola and the bottom is always the line. And that's consistent no matter where I draw that rectangle. I know that horizontal rectangles won't work, and the reason is because, I'm going to erase what I'm about to write here in a minute so that the drawing isn't too busy, but the reason is because if I draw a horizontal rectangle here, then the right boundary is the line and the left boundary is the parabola. But if I slide up and I draw the rectangle up here, then the right boundary is the parabola and the left boundary is the parabola. Like the boundaries change as I slide that rectangle up and down. So that's how I know that horizontal rectangles won't work. So we're using these vertical rectangles. It has a delta x width, and the length is the top y minus the bottom y. So that's the top curve is 2 minus x squared minus the bottom curve is x. So there's our length. And we can put together now the area of the sample rectangle. So our delta area, delta A, length times width, is 2 minus, I'm going to write it as 2 minus x squared just because then my terms are kind of in order, in this case in ascending order instead of descending order, but you can obviously write those terms in any order you like. So there's length times width. Width is delta x. And remember, once I have the area of this sample rectangle, then the integral pretty much writes itself. So the area, let me Bring this back a little bit. So the area will be the integral 2 minus x squared dx. Delta x turns into dx. The only thing we're missing are the limits, and the limits are going to come from finding these points. Maybe you've already kind of had that notion as you kind of considered this problem initially. So for the limits, we're going to have to find those intersections. So we're just going to set these curves equal to each other. X is equal to 2 minus x squared. If I get all of my terms on one side, we have x squared plus x minus 2 is 0. There's a quadratic. You could solve it in whatever your favorite method is. In this case, I think it can be factored, so I'm just going to go ahead and factor it. We get x plus 2, x minus 1 equals 0, and that gives us the values x equals negative 2, x equals positive 1. And if you look at the graph, that seems plausible, right, that it could be around there. My drawing is definitely not perfect, so but those are our values that we get. So those are our limits. We're integrating from negative 2 to 1, putting those on the integral. Now the hardest part is done. Now we're going to integrate and evaluate. So integrating this, it's a polynomial, no u substitutions are needed. We get 2x minus 1/2 x squared minus 1/3 x cubed, and then we evaluate from minus 2 to 1. So let's see. If I plug in 1, I'm just going to go ahead and evaluate each term when I plug in 1. So the first term, when I plug in 1, is 2 minus, that'll be 1/2 minus 1/3. And then minus, I'm going to plug in negative 2. Plugging in negative 2 gives us negative 4 minus 1/2 times negative 2 squared is positive 4. So 1/2 times 4 is 2. And then minus, let's see, negative 2 cubed is negative 8. So this term will be a negative 8/3. And you could just throw this in the calculator at this point, and when you do that, you'll get 9/2. All right, let's try another one. This one's a little bit different, just because they give us just two functions like the last one. So it's similar to the last one in that sense. But they say find the area of the region bounded by these graphs. There's sort of two parts to this region. I mean, they're connected, right? It's sort of contiguous through this point where they touch. But we need to consider these two regions separately. So here's one region. And then here's another region. Or one part of the region and the other part of the region. So this part on the left, I'm going to call this A1. We'll find that area. And again, we'll see that vertical rectangles are how we want to go. Actually, I'm going to use a different color just to make it show up a little bit better. And I'll call this other region, we'll find that area, call it A2. And again, we're going to want to use vertical rectangles. And of course, when we use vertical rectangles, that means the width is delta x. So what's different about these two parts of the region? What's different is which curve is on top and the limits, right? So they share a limit, right? The blue region looks like it ends at x equals 0, and that's where the the green region kind of picks up where that leaves off. But they have different, the left region of A1 is obviously different than the right region of A2. So maybe what we can do is find these limits. And we'll do some of that algebra first. So we're going to find the intersection of these curves to get the limits of this integral, of these integrals that we need. So I'm going to set these equal to each other. We've got 3x cubed minus x squared minus 10x equal to negative x squared plus 2x. I'm going to throw all my terms on one side, so I get 3x cubed. If I add x squared, the x squareds disappear. If I subtract 2x, then I have a minus 12x. And let's factor this. We could take out a 3x, and then we have x squared minus 4 equal to 0. And x squared minus 4 is the difference of squares. So we got 3x, x minus 2, x plus 2. And that gives us our limits. So x equals 0 to negative 2. So the blue region here is we're going to integrate from negative 2 to 0, and the green region will integrate from 0 to 2. All right, so let's consider these regions separately. So for A1, the top minus bottom, that length is equal to 3x cubed minus x squared minus 10x minus, and then the bottom curve is the parabola, minus x squared plus 2x. That will simplify to 3x cubed minus 12x. And so delta A1 is length times width, so 3x cubed minus 12x times delta x. Over here on the right side, this green region, our length, so the curves have just sort of flipped, right? The top curve now is the parabola, and the bottom curve is the cubic function. So this is negative x squared plus 2 minus 3x cubed minus x squared minus 10x. And of course, when you reverse the order of subtraction, when you're working with the same expressions and you're just reversing the order of subtraction, you're going to get just the negative of what we already got. You could check this, but you're going to get 12x minus 3x cubed. So our delta A1, the area of that sample rectangle in the green region, or sorry, A2, is 12x minus 3x cubed, all multiplied by delta x. So right now, we really have done, the hard part. We have set things up. We have the expression that gives us the area of each sample rectangle. And from here, the integrals pretty much write themselves. So A1, this is the integral of 3x cubed minus 12x dx. And the blue region had bounds of from negative 2 and 0, so we're going to integrate from minus 2 to 0. We can integrate this. Using the power rule, the general power formula, we get 3/4 x to the 4th minus 6x squared. And if I plug in 0, the upper limit, every term has every term has a factor of x, so the whole thing zeroes out if I plug in 0. And then plugging in negative 2 looks like this. I'm going to show you, and you might already be familiar with this or remember it from when we had to do it in Calc 1, but your calculator can evaluate expressions for a given input. So what I'm going to do, I'm going to put this expression, 3/4 x to the fourth minus 6x squared, into my y1 function in the calculator. So 3/4 x to the fourth minus 6x squared. And then I'm going to quit to home, and I want to evaluate that at -2. So I'm going to hit the vars button. I'm going to arrow over to y bars, select function, and then I put mine in y1, so I'm selecting y1. And then this is function notation, so open up parentheses, put in your input, -2, close your parentheses, and we get -12. So this is 0 minus -12, or 12. Now, an area of a region is always positive. If you get a negative value when you find the area of a region, it means there's a mistake somewhere. It does not mean just make your answer positive and it's fine. It means there's an error and you should find it. So here we do in fact get a positive area, but I wanted to kind of bring that up because sometimes that happens. Making an error when you're doing an area problem can lead to a negative result, and at least then if you got a negative result you'll know that, oh, there's something wrong and we need to find what it is. So there's the A1 part. A2, well, this is the integral from 0 to 2, 12x minus 3x cubed. It's really the same expression, so when we integrate using the power rule, we get 6x squared minus 3/4 x to the fourth from 0 to 2. We're going to plug in 2 first. And then when we plug in 0, again, we're going to get 0 because there's a factor of x in every term. It will be probably unsurprising that when we evaluate the expression at 2, we get 12. So we get 12 minus 0, which is 12. So these two regions have the same area. And now we wanted the area of the region bounded by these graphs. So the last thing to do is we're just going to add them together. So our area is 24. All right, let's try one more. And right away, I guess I've given away the surprise, but this is going to be an example where we need to use horizontal rectangles. When you're doing a problem and it looks like they're switching up the variables and they decide to give you the function as x equals, you know, some expression with y's, that's a sign that they could actually just be helping you out a bit. If you need to use horizontal rectangles, then that length is a horizontal length, which means you're going to get you want an expression with y's when you're using horizontal rectangles. So it could be that they're helping you out a little bit. The first graph here, x equals 3 minus y squared. You know, our calculators are designed to graph things that look like y as some function of x. So you could use your calculator to help you out with this by solving it for y, but you'll have to do two graphs, because when you solve it for y, you'll have to take a square root, and you'll want to graph the positive root and the negative root to see the whole curve. But we could also just sort of analyzing this, we could see this is definitely a parabola, right? The y is squared, the x is not. It's a negative y squared, so that's going to open to the left. And it's like, this is the same as negative y squared plus 3. So that's the parabola that opens to the left, but shifted to the right 3 units. And you can confirm that if you graph it on the calculator. So this looks something like this. Definitely not my best parabola, but you know, we just want to get a sense of what it might look like. And then the other function is y equals x minus 1. So there's a line, slope 1, y-intercept of negative 1. So that looks like this. And we can see that this does sort of properly bound a region. Looks like this. Now, see if you can't come up with an explanation for why we know that we cannot use vertical rectangles. Or I guess it's sort of possible to make vertical rectangles work with a lot of extra work. But why are vertical rectangles not preferred? Now, if you did want to draw vertical rectangles, over on this side, the length, the top minus bottom, is the line minus the parabola. But as I move through the region, and I move way over here, now top minus bottom is parabola minus parabola. The boundaries change within the region, and that is not a desirable scenario. So what we're going to do is use horizontal rectangles. And if you take a look at this horizontal rectangle, you know, and now imagine sliding it up and down through the region. The right boundary is always the parabola, and the left boundary is always the line. So the boundaries remain consistent no matter where we kind of slide it through the region. That's how we know that horizontal rectangles will work. Horizontal rectangles have a vertical width, that's a delta y, and the length is right minus left. It's the right x minus left x, where each of these, you know, the right x and the left x, they are expressions with y. So the right x, well, they gave us what x is in terms of y. The right x is 3 minus y squared. The left x, we just do a little, you know, tiny bit of algebra. Let's rearrange this to solve for x. If y is x minus 1, then x is y plus 1. So that's what we're going to subtract here. I'm subtracting the whole thing, so notice I've got parentheses. And simplifying this, we get 2 minus y squared. So that's the length. That's the length, and that means that the delta area, delta A, length times width is 2 minus y squared times delta y. So note that when we use horizontal rectangles, the width is a delta y. That means that we're going to integrate with respect to y, and we have to have an expression of y's. We integrate y's with respect to y. So this integral, when we write it out, we're going to integrate 2 minus y squared dy. And what we need now are limits. And because it's a dy, we have to be careful. These are, that means that we need y limits. Right, we're imagining that we can slide that blue rectangle up and down through the region. So I want to know what's the highest, you know, the furthest up that we can slide that rectangle, you know, so where do the curves intersect up there, and what's the lowest point we could slide that rectangle, so what's the intersection down there. And we're going to find the intersection the same way. We're going to set these curves equal to each other. So y plus 1, that's the line, is equal to 3 minus y squared. Gathering all of my terms on one side, y squared plus y minus 2 is equal to 0. This will factor. Plus 2 minus 1, and we get y equals negative 2 and y equals positive 1. And that looks plausible, right, with how the sketch is. So those are our limits from negative 2 to 1. I'm going to scroll back up here and put those limits in the integral. And now, again, this is a polynomial, so the integration is fairly simple. When we integrate, we'll get 2y minus 1/2 y squared minus 1/3 y cubed. And our limits from -2 to 1. We're going to plug in these values. If I plug in 1, then the expression is 2 minus 1/2 minus 1/3 minus, if we plug in -2, let's see, I'm going to actually just throw that in. 2 times -2 minus 1/2 times -2 squared minus 1/3 times -2 cubed. And let's see, if you evaluate this part in the calculator, you'll get 7/6 minus, and if you evaluate that part in the calculator, you will get a -10/3. So 7/6 plus 10/3, and that simplifies to 9/2. Okay.